First, let me say I apologize for not being there with you to go through this math together in person. Today we're going to be talking about variation equations. There are different types of variation equations. These are not difficult equations. You just have to be able to read the words, identify the type of variation, and write the corresponding equation. Then you'll be asked to find a few other pieces of information. So the first type of variation that we're going to talk about is direct variation. Now, variation is the relationship between two variables, in this case x and y, and direct variation is written as this type of equation. Y equals k times x. Now, k is your constant of variation. It is a variable that represents the proportionality, the relationship between y and x. This is just a linear function. Now, k cannot equal 0 because if k equals 0, we see that the right-hand side will be 0. So what you'll have to do is you'll have to read when it says y varies directly as x, or y is proportional to x, and turn that into this equation. Look at the first example. It says that y varies directly as x. The key is to see how y varies. Then we would write the corresponding equation. Y varies directly as x. Now, the key is to substitute in values for x and y to be able to find that constant of variation k. So we have been given y equals 45. So I'm going to substitute that in for y. And we have been given that x equals 5. So now this is just a linear equation that we can solve for k. How do we do that? We divide both sides by 5, and we get that k equals 9. Now, I'm going to take that constant of variation and I'm going to substitute it back into the variation equation. So I have y equals 9 times x. So that is your variation function. Now, you have been given an additional piece of information. You have been given x equals 13, and we're trying to figure out what y is when x equals 13. So all I'm going to do is substitute into your variation function y, what we're looking for, equals 9 times 13. So what is y in this case when x equals 13? Y is 117. So what you notice is that for direct variation, if x is increasing, then y will be increasing. So if I substitute in values for x, as I substitute in larger and larger values, y will become larger and larger as well. Similarly, if I substitute in smaller and smaller values for x, meaning y is decreasing, then x is decreasing, then y also will be decreasing. This is the pattern that you will recognize in the relationship between x and y for direct variation. Now, we can also increase directly with powers of x. So how would I read this? This would be y varies directly as x, in this case, to the nth power. So you can raise x to a power. The second type of variation is called inverse variation. It's still a relationship between x and y, but notice the pattern. So here is the equation for inverse variation. Again, x cannot equal 0. How do we read that? We read it as y varies inversely as x. So when you read those words, you should think of this equation. So here let's look at an example. Given y varies inversely as x, so again, what do we write? Y varies inversely as x. We put x in the denominator because we're inverting the placement of x. So here is your inverse variation equation, and we need to find k. So if I'm trying to find k, I'm going to substitute in what I have been given for y and x. So y is 6. K is the constant of variation that we're finding, and x is 3. So if I want to solve for k, all I have to do is multiply both sides by 3, and I get that the constant of variation k equals 18. So now I have to write my variation function. So I'm going to take the general form, and I'm going to substitute in my constant of variation. This, again, is the variation function for this relationship that you've been given. Now, you have been given some additional information which will allow you to find a y given a value of x. So I'm going to substitute in x equal 9, and that would give me y equals 2. So when x is 9, y is 2. Now, what is the pattern that you notice for inverse variation? If you were to substitute in larger and larger values of x, then what will you notice about y? Y would be decreasing. If you substitute in smaller and smaller values of x, then what do you notice will happen with y? The corresponding values of y would be increasing. So this is the pattern that you will see for inverse variation. Okay, now for the last page, page 3 of the 3.7 notes. Here we're going to talk about solving problems involving joint variation for starters. So if you are given the words y varies jointly as m and the square of n and inversely as p, we would write that as an equation. Y varies jointly as m and the square of n and inversely as p. So there's your variation equation. Now let's substitute in what we know. We know that when y is 15, k is that constant of variation that we don't know, and when m is 2, n is 1, and that's to be squared, p is 6. So if I substitute in all the information given, I can solve for my constant of variation. 2 times 1 is 2 over 6. I can simplify that as 1 over 3, giving me 15 equals k over 3. Then I'm going to multiply both sides by 3, and I get my constant of variation, k equals 45. I'm going to substitute that back into my variation equation. K is 45 times m times n squared all over p. I should erase that a little bit. Now, we have been given additional information and we are being asked to solve for y. So we are finding y when m is 3 and n is 4 and p is 10. So I'm just simplifying the right-hand side. 45 times 3 times 16 over 10. And if I multiply everything in the numerator, oh, that's 10, and divide by 10, I'm going to get y equals 216. And we're done. So, how can you determine or identify direct or inverse variation? Well, for starters, you have to know the direct variation general form of the equation, the inverse variation general form of the equation. From that, you can solve for k. So if I were to solve for k in this equation, I would divide both sides by x, and I'd get k equals y over x. So that's how you identify the constant of variation for the direct variation problems. If I'm looking at my inverse variation general equation, I would be multiplying both sides by x. So then k would equal x times y. That is how you identify the constant of variation. So if you're looking at example 7, you are being asked to determine whether each data set, so you have two tables of values, and you are trying to determine if those tables of values, that data represents direct or inverse variation, or perhaps neither. So, keeping in mind k, we can solve for k for each of these sets of points to determine the variation. Or you can just kind of look at the pattern for x and y, and at the very beginning we talked about if they both increase or if they both decrease, it's direct variation, and as x increases, y decreases, or as x decreases, y increases, we have inverse variation. So let's go ahead and just kind of look at it. If I look at my x values in my first table, I see that my x values are increasing. If I look at my y values in my first table, I see that my y values are decreasing. So you can see that perhaps this is inverse variation. However, we have to double check to make sure we have a constant k. So we actually have to find k. So we can look at, we think it's inverse. So if it's inverse variation, we need to see if this is true for all x and y pairs. Is that k constant? So for inverse variation, k equals xy. So let's go ahead and multiply x times y for each of those sets. So this would be 6.5 times 8, which is 52. Now let's look at the next pair of xy. That's 13 times 4, which is also 52. But we can't assume that the last set of xy values also gives us 52. But if we do the multiplication, we see that we have a constant of variation for this problem as 52. So if I were to write the inverse variation equation that corresponds to this, it would be y equals 52 over x. So I have found my inverse variation function. So this one, in fact, is inverse. But don't automatically assume because both the x and y are going in the same or different directions that it's direct or inverse. We actually have to check for the constant of variation. But that gives us a clue as to which one we want to check first. So let's look at the next one. In this table, we investigate our x values and we see they are increasing. If we investigate our y values, we see that they are also increasing. So we think perhaps it's direct variation, but we have to confirm that there is a constant of variation k. Now the relationship for k for direct variation is y over x. Now don't get confused by the fact that you say direct and you see a ratio over here on the right hand side. This is for k. This is not the direct variation function where y is isolated on the left hand side. But let's go ahead and investigate our k's. So if I take the ratio of y over x, what do I get? 6. If I take the ratio of y over x for the second set of ordered pairs, I also get 6, but I do have to check the third one to make sure that that k is constant. I do get 6. So I see that k equals 6. That constant of variation is 6. So this is in fact direct variation, and I can write the variation function as y equal 6 times x, and I have my variation function. I hope this lesson made sense. Now go try the My Math Lab homework. My apologies for having to upload separate files. I had an issue with my computer, so hopefully now we'll be able to do page 2 and page 3 of the 3.7 notes on variation. So now we're going to talk about another type of variation. We can combine both direct and indirect variation to get combined variation. So notice direct variation allows us to have the x in the numerator, so y equal kx was direct, y equal k over a variable was inverse. So if I combine the two, I get combined variation, which is this y equals k times x over w. Now you may wonder about the k's. Well, we can combine them into one constant of variation, so you don't really have two k's. So let's look at how we would write a combined variation function given the words. So A varies directly as B and inversely as the square of C. So this would be over C squared. So now we have A varying directly with B and inversely as the square of C. Now this corresponds to what we just said up here, where y varies directly with x and inversely with w. So this is the corresponding variation equation. Now, again, we're just going to substitute in the values that we've been given. So we have A equals 7. K is the constant of variation that we're trying to find. B is 9. And C is 6. So we're going to square 6. So if I simplify, actually perform the multiplication on the right-hand side, I have this. Now notice we can go ahead and simplify further. 9 goes into 9 once, 9 goes into 36 4 times, giving us 7 equals k over 4. If I want to solve for k, I'm just going to multiply both sides of the equation by 4, and I get k equals 28. Now I'm going to come substitute that back in to get my variation function. So A equals K we found to be 28 varies directly with B and inversely with the square of C. Here is your variation function. Now, we have been given additional information that will allow us to solve for one of the variables using this variation function. We're trying to find A. When B equals 4, so B equals 4, substitute in 4 for B, C equals 8. So if I continue to solve for A, I get 24 times 4. Well, I'll look at this. I can simplify after I evaluate the denominator. 4 goes into 4 once. It goes into 64 16 times. So that's going to give me A equals 28 over 16, which I can simplify even further, 7/4. So there's my answer to this problem. Now, the next type of variation that we're going to talk about is called joint variation. So joint variation is the relationship now among three variables. Now, it resembles direct variation in the sense that everything is in the numerator. Y equals our constant of variation K times X and Z. So we read this, Y varies jointly as X and Z. So we're going to solve our variation problem the same way. The only difference is we're going to now use an application. So this is fun. The volume V of a cone varies jointly as the area of the base B and the height H. So here is how we would write those words as a variation equation. Now let's substitute in what we know. V is 12 pi feet squared. That is going to equal K, which we still have to find. We've been told that the base is 9 pi, and we've been told that the height is 4. So I'm just substituting in what I know. Now, if I simplify, I'm going to get 12 pi equals 9 times 4 is 36 pi K. If I divide both sides by 36 pi, what is K going to be? K is going to equal 1/3. So now I'm going to substitute that back into the original variation equation that I wrote from the words, and I'm going to substitute in for K 1/3. So V equals 1/3 times the base times the height. Here is my variation function. Now, you are being asked to find the variation function in terms of B. So we are solving for B. So if I need to solve for B, given this information here, so we're being asked to find B given this information, I'm going to substitute in 24 pi. I'm going to substitute in 9 for H. I'm going to simplify the right-hand side. And so that is going to give me 24 pi equals 3b. Last step would be to divide both sides by 3. And so I get that b equals 8 pi. So the volume is 24 pi feet cubed, and the height is 9 feet. The area of the base is 8 pi feet squared.